Okay, I'm recording this so Wyatt, Madison, and Lydia get a chance to see it. And welcome back after Easter. I hope you had a decent break. Today we're going to begin talking about one of the last remaining topics for the school year. We don't have that long to go. And the remaining topics that we're going to address, we're going to be talking today about, we're going to begin studying oxidation and reduction. And then we're going to move into something called electrochemistry. And finally, we'll wrap up the year talking a little bit about what's called organic chemistry. Just a little bit. We're going to not go into great detail because organic chemistry is a course that you can take for a full year in college. Matter of fact, it's one of the tougher chemistry courses for undergraduates because that's the one that they try to weed you out when you're going to medical school. That's a tough class, but it's really interesting. So let's talk about oxidation and reduction. We've touched on these things in the past, and it's time to take maybe today just to review oxidation and reduction, because all of our business of making electrochemical cells and all of our business of studying electrochemistry comes from this idea of oxidation and reduction. If you remember correctly, we had a case where we could see something like a sodium atom, and that would go and lose an electron, and that process was called oxidation. And we, like I said, when we were studying reaction types way back at the beginning of the school year, we mentioned these. So if something loses electrons, that's oxidation. And then if I take something like, let's say Cl2, and I give it 2 electrons, well, what I'm going to do is form 2 chloride ions. So what's happening in this case is the chlorine is gaining electrons, and those gaining of electrons, that's called reduction. Now, if we want to go ahead and write the complete reaction that's taking place here, we want to make sure that our electrons are the same on both sides of the arrow. So what we do here, if we want to balance this, is multiply this top equation by 2. That'll give me 2 electrons on the product side, 2 electrons on the reactant side, and what we're going to see here is we can write the balanced equation. So I'm just going to add these together. So I'm going to get 2 sodium atoms plus Cl2 to give 2 NaCl, sodium chlorides. Now, one of the things I want to try to make you aware of is how to determine what's called the oxidation state. Of each of the elements in chemical compounds, because we're going to have to be able to identify that when we start looking at these things. Oxidation state, it's kind of like, well, for ions, it's the same thing as their charge. So for a sodium cation, sodium plus 1, its oxidation state is +1. When it's a pure element, though, just sitting there by itself, not bothering anybody, not reacting, its oxidation state is 0. It has 0 charge on it. So elements, let me write that over here. This is an easy thing to think about. Elements in their standard states the oxidation state is 0. Some people also say oxidation number. That's another thing, oxidation number. When we refer to the number, we call it the oxidation number. So the oxidation number on sodium here would be 0. On chlorine here, this is an element in its standard state. So that's 0 and that's 0. Now, obviously, when this loses an electron, Now this gets +1 oxidation number. It's in the +1 oxidation state. It's a charged ion, and the charge is +1. Chlorine over here is 0 oxidation number. Over here, -1. So -1, each one of these is a -1. That also is an ion, so the oxidation number is the same as the charge. So let's take a look at one. Maybe you can identify what's going on with some of these. Okay. What have we got going on here? First of all, this is an oxidation. And what's the oxidation number on 0, right? How about down here? 0. Can you see? Because those are elements in their standard states. Hi, Maddie.
Hey.
I marked the absence. Did you stop into attendance? Okay, very good. How about over here? +2, yeah, +2, good. That's the oxidation state of the magnesium. It's also the charge on the ion, okay? And then down here, now I've got these two oxides. So what can we say about that? Each one is -2, yeah. -2 for each of the oxygens. It's also the charge on the ions. Now, if I want to balance this equation, what do you think I'm going to do? If I want to add these equations, how can I get rid of all the electrons?
You asked my slide.
Correct, yeah, multiply that by 2, and then we're going to have the overall reaction, 2 magnesiums plus O2 to give 2 MgO. So when you look at this, these are the types of reactions where you need to look at them, not necessarily go through these steps, but just learn to identify them. So we know that elements in their standard states have oxidation numbers of 0. Okay, that was our rule number 1 here. The next one is oxidation states, or numbers, on ions are the same as the charge. So remember, way back in the day, we learned various ways to look at the charges on ions. We look at the electron configuration, how they can get a full octet. We just said that group 1 gets a +1, group 2 gets a +2, jumping over to the nitrogen group, that gets a -3, etc., -2, -1. So we can look at those ions right away in ionic compounds and pick out their oxidation states. So I don't need to go through all this. I know magnesium's in group 2, so it's in the +2 oxidation state, and I know that oxide gets a -2. So that's a little bit of review. Now the trick becomes, what happens when I have covalent compounds? How do we deal with covalent compounds? Well, let's talk about those for a little bit. I'll pick out some chemical compounds here and take a look. Well, let's take a look at some simple molecules that are covalent, like CO2. Now, what we're going to do, we know that oxygen normally, if you look at the periodic table, normally gets a -2 charge as an ion. There is a case in peroxide where it doesn't, but we didn't really study that. So we still look at oxygen as if it was -2. So we have 2 of them, so 2 times -2, that's going to give a -4 total. So my oxidation state of my carbon has to be +4. Now, this does not mean this is the same as a charge. This is just like a formal way of trying to understand in chemical reactions, if these numbers change, then one thing's going to be oxidized and one thing's going to be reduced. So anything that, for example, burns, like in a combustion reaction, we can calculate that one thing is oxidized and one thing's reduced. We'll look at some of those examples. So if you grab one of these books, grab one of these. If there's not one under the desk, we'll hunt around for it. And turn to page 524. And I want to look at these rules together. Okay, guys, this is on page 524. Can't see that here with the little camera. So let's take a look at these rules together, because these are the things that we're going to have to use when we start looking at some homework problems here. It says the oxidation state of an atom in an uncombined element is 0. Now, we already said that one, so that one was easy enough. The oxidation state of a monatomic ion is the same as its charge. So things like O with a 2+ charge, or F with a minus charge. The oxidation state is the same as its charge. Another one might be aluminum, the +3, etc. Okay, now, this is where you need to start really following along with these rules. Oxygen is assigned an oxidation state of -2 in most covalent compounds. The exception is with peroxides, but we're not going to worry too much about peroxide, and that would be a -1. But for our purposes, you're always going to see, oh, that should be a minus charge. You're always going to see a oxygen with a -2 oxidation state when it's combined with something else. Number 4. In its covalent compound with nonmetals, hydrogen is assigned an oxidation state of +1. So hydrogen, we're always going to say, has an oxidation state of +1 when it's combined in a covalent compound. Okay. In a binary compound, the element with a greater electronegativity is assigned a negative oxidation state equal to its charge. So for example, if I had something like this, SF6, you take a look at SF6, this is a covalent compound. There's no metal here. And the more electronegative atom here is fluorine. Matter of fact, that's the most electronegative atom in the universe. So I've got 6 of them. Each one gets an oxidation state of -1. So that means my sulfur has to be a +6 oxidation state. And again, we're just using this as a method to get to something else, to be able to determine what's oxidized and what's reduced. It says here, this is number 6, for an electrically neutral compound, the sum of the oxidation states must be 0. So SF6 is a neutral compound, so we have 6 times -1 and a +6. So together, all of those things will cancel out. And finally, if you have a polyatomic ion, the sum of the oxidation states must equal the overall charge. Let's take a look at one, and I'll show you what I mean. Let's take a look at a polyatomic ion. That's called the nitrate ion. We've seen it many, many times. And we can pick out all the oxidation states for the elements in here. And in this case, they have to add up to -1, because that's the charge on the polyatomic ion. So I've got 3 times a -2, that's -6. And this has to give me a value that, when added to -6, still leaves a -1. So that's going to be 5 plus 5. So in that case, the oxidation state's +5. In other compounds, it can change. Like if I have this, N, well, let's take a look at NH3, right? NH3 still has a nitrogen. Each of the hydrogens gets +1, so 3 times a +1 is +3, and this nitrogen here would be -3 oxidation state. So we treat them kind of like charges, but really it's for bookkeeping electrons. So why don't you go ahead and take a look at the bottom of page 525. I'll put this on pause. The bottom of page 525, and see if you can come up with those oxidation states for those five chemical compounds. I'll pause this. Okay, let's take a look at these particular covalent compounds or polyatomic ions. First one is sulfur trioxide. So by now, you're going to see oxygens in these things, and each one's going to be -2. 3, -2, -6. Remember, they have to add up to 0. So sulfur will have the oxidation state of +6. So check this one out. This is the sulfate ion. And the sulfate ion, I've got 4 times -2 is -8. The whole thing has to add up to -2. So this is going to be +6 again. +6 oxidation state. And then our next one is N2O5. All right. We got 5 times -2. That's -10. And I got 2 of these. So what does each one have to be? +5. See? Easy stuff. PF3. Phosphorus trifluoride. Fluoride, very electronegative, obviously. 3 times -1, -3, +3. Cancel out. And then finally, C2H6. Now remember, hydrogen in these types of compounds is +1. So I have 6 times +1 is going to be +6. Now the carbon, I have 2 of them. So each one will have a -3 oxidation state. Pretty easy stuff. We'll take a look at some of these again for homework. I want to take a look at an actual chemical reaction and show you how we know which things being oxidized and which things being reduced. Just take a little combustion reaction here. We'll do CH4 plus O2 to give CO2 plus H2O. And let's make sure everything's balanced here. 4 hydrogens, I've got to put a 2 there. I got 1, 2, 3, 4 oxygens, so I put a 2 there. And we're all balanced. Now, let's take a look here. Let's identify the oxidation numbers in all of the different chemical compounds. Well, this is 0. That's an element in its standard state. And over here, we have, each one's going to be a -2, and each one's going to be a -2 on that side, because now they're part of chemical compounds. In this case, each one of these is a +1, so this has to be a -4 oxidation state on that. And over here, I have to have a +4 oxidation state. So you can see that the carbon is losing electrons in this reaction, and the oxygen is gaining electrons. So the oxygen is being reduced, and the carbon's being oxidized. And that's all. If you can keep track of those things, you are going to be in pretty good shape. Let's do one more, and then we'll look at some problems. Our old famous reaction. Take a look. 0, 0, and over here, each one of these is going to have in the +1 oxidation state, and this is going to be -3. So let's take a look. I have nitrogen, N2, turning into 2 nitrogens. I don't want you to think this is a real charge, but I'll just put it up here. So that had to gain electrons. Right? We got 6 of them. So all of my numbers have to add up. 2 times minus 3 is 6, 6 electrons. So we see that nitrogen is being reduced. It's gaining electrons. Let's look at hydrogen. I've got 3H2, and that's 0. So I have a total of 6 hydrogens. So over here, I'm going to have 6 H pluses plus 6 electrons. And this then is being oxidized, losing electrons. Now, I'm going to give you some vocabulary, and then we're going to shoot into looking at some problems. This is a reduction reaction. This is an oxidation reaction. Now, if this is the reduction reaction, nitrogen is called the oxidizing agent. In other words, this is the agent causing the other thing to be oxidized. Now, the thing that is being oxidized is causing the other thing to be reduced, so this is called the reducing agent. So later on, when we start looking at more reactions, they'll say, hey, which one's the oxidizing agent? Which one's the reducing agent? And it's the opposite of what's happening. If this is being reduced, it is the oxidizing agent. If this is being oxidized, it is the reducing agent. So let's take a look in the back of your chapter. And we'll take a look at a few of these. How about we take a look at page 545 and go through 13 through 22, 13 through 21, the odd problems, and work on those. Okay.